Hello everyone, this is Nur Imtiazul Haq. I am going to present our paper naming BIOCAD, Bio-Inspired Optimization for Classification and Anomaly Detection in Digital Healthcare Systems, which is recently got accepted to be published in IEEE International Conference on Digital Healthcare 2021. So these are the contents of my presentation. At first, I'm going to discuss about the motivation behind choosing the problem domain of proposing an integration detection system in the smart digital healthcare. After that, I'll highlight the main contribution of our proposed anomaly detection system and the classification model. After that, I'll provide a short overview of the proposed framework. Then I'll talk more about the methodology, evaluation, and experimental results. Finally, I'll conclude my presentation by discussing the future plans of extension. So the traditional healthcare sector is experiencing high costs due to patient monitoring, consultation, hospitalization, and treatment, which is proven by a recent report stating that United States is experiencing $4 trillion of expenditure in the healthcare sector. To reduce this cost and ensure pervasive healthcare, the modern healthcare system is using Internet of Medical Things based network to collect patient vital signs from wireless body sensor network, then sends these sensor measurements to an artificial intelligence based controller. After that, it eventually actuates the implantable medical devices for automated medical delivery. Identification of the right disease is mandatory for right medication. That's why machine learning based controllers are mostly used in smart digital healthcare due to its high prediction accuracy. But misclassification is hazardous in smart digital healthcare system because it might eventually threaten the patient's life due to inaccurate classification of diseases. Again, open network communication for sensitive medical data transfer is giving rise to vulnerabilities and various security concerns. And that's why anomaly detection systems are embedded with the disease classification systems in the smart digital healthcare controller. Although the machine learning models are extensively used in various cyber physical systems, anomaly detection, classification, etc., but the main problem arises due to their high dependence on the hyperparameters tuning. So various optimization techniques are being used to get the best out of these machine learning models by finding the optimal hyperparameters to minimize the cost functions. In our work, we have used the bio-inspired stochastic optimization algorithm due to their high computational efficacy. And these bio-inspired algorithms are unique heuristic soft computing approaches that imitates the nature's strategy as a process of constraint optimization. So in this work, we actually used or imitated the behavior of the gray wolf, whales, firefly, etc. As I discussed earlier, in this work, we are targeting both the disease classification and the anomaly detection of smart digital healthcare system. So as disease classification system, we are considering support vector machine and neural networks due to their high prediction accuracy, and they are extensively used by the recent researchers in the medical domain. And for the anomaly detection system, we considered the novelty detection technique naming 1+SVM, which shows very good performance for detecting zero-day attacks. And also the density-based spatial clustering of application with noise, which is a clustering algorithm, is also being explored for generating anomaly detection system for the smart digital healthcare. And for hyperparameter tuning of these machine learning models, we have used three optimization approaches, which are the gray wolf optimization, whale optimization, and the firefly optimization. So to highlight the main contribution of our work, we can say that we have investigated various machine learning algorithms both for classification models and anomaly detection models, and designed a real-time smart digital healthcare deploying them. And our proposed framework has been evaluated based on the classification and anomaly detection capability, and also based on the scalability of our system. We proposed a novel fitness function for a hyperparameter optimization of both the clustering and the novelty detection technique that we considered for zero data detection. And our proposed framework has been evaluated and been verified using 3 state-of-the-art datasets, naming the Pima Indian diabetes dataset, Parkinson dataset, and University of Queensland vital sign dataset. The basic architecture of the proposed BIOCAD framework is pictured in this figure. Here the controller module leverages the historic data points of various patient vital signs data to train the machine learning models, and works as an optimal classifier and anomaly detector. The wireless body sensor network measures patients' vital signs through plethora of sensors and provides real-time sensor measurements to the controller. The controller module has 2 submodules. One is the classifier and anomaly detector, another one is the bio-inspired optimization module. The classifier and anomaly detector module either uses a support vector machine or a neural network to as a disease classification model, and uses DBSCAN or one-class SVM model for anomaly detection. All of these models have several hyperparameters to be tuned. For instance, support vector machine has 2 hyperparameters, naming C and gamma. For each misclassified data point, the C hyperparameter gives a penalty. And the gamma parameter regulates the influence decision of a single training point. The neural network model has 2 hyperparameters to be tuned. One is the number of nodes in the hidden layer and the number of hidden layers. The DBSCAN, on the other hand, uses the minimum number of points and the radius as their hyperparameter. The one-class SVM, like SVM, has 2 hyperparameters to be tuned. One is the nu, another one is a gamma. And all those parameters are passed to the bio-inspired optimization module, which uses either Grey-Wolf, whale, or Firefly optimization technique to optimize the hyperparameters. And those hyperparameters are then sent to the controller. Controller then retrains the model, and during this process, if the controller has found any abnormality in the sensor measurement, it notifies the network security administrator. So these are the 3 bio-inspired optimization technique that our framework can use for optimizing the hyperparameter of the considered machine learning models. I'm not going into detail, but all of these 3 models, like this Grey-Wolf, the whale, and the Firefly optimization techniques. As I discussed earlier, we experimented with 3 datasets, naming the Pima Indian dataset, the Parkinson dataset, University of Queensland vital sign dataset. The Pima Indians diabetes dataset contains several medical prediction variables like patient's age, BMI, the number of pregnancies, insulin level, etc., and one target variable, which is the status of diabetes of a patient. The Parkinson dataset, on the other hand, is composed of a range of biomedical voice measurements from 31 people, where 23 of them are affected with Parkinson's disease. The University of Queensland vital sign dataset records anesthetic patient monitoring data from 32 cases, and ranging from 5 hours to 13 hours. So we have actually used a portion of the dataset for our for verifying or validating our proposed framework. And our framework has also the capability of pre-processing the dataset. It at first splits the overall dataset by 75% and 25% train test split. for validating the performance of the machine learning model. It is also capable of handling the missing data through various techniques. And for computational efficacy, it uses principal component analysis based feature iteration technique. So this table is for showing the performance of our proposed BIOCAD framework for hyperparameter optimization of the classification models. So from the table, it is evident that on both Pima Indians diabetes dataset and the University of Queensland vital sign dataset, all the optimization models perform significantly well, except for the GRAILF on the Pima Indians dataset for support vector machine-based classification model. And however, but none of these models demonstrate good performance on the Parkinson dataset. The high false negative rate is mainly responsible for this performance degradation, we assume, and as indicated by the low recall value. Increasing the number of agents and the number of iteration did not also help to prevent getting trapped into the local optima. So all the models performed significantly well on for the false positive cases, which is proven by the perfect precision scores. As the dataset are imbalanced dataset, the F1 score might be the best parameter for the comparison, and based on the performance analysis of both support vector machine and neural network models, it seems that the GRAILF, well optimization algorithm outperforms the GRAILF and the Firefly optimization in most of the cases. So the anomaly detection model's performance is evaluated on both benign and the anomalous data. So anomalous dataset is generated from the benign dataset by launching false data injection attack based on one of our previously published work. Although correctly identifying the anomalies is the primary task of the anomaly detection model, it is not desirable to experience a lot of false alarm. So from the table, it can be observed that on the Parkinson and the University of Queensland vital sign dataset, all three optimization models perform significantly well on both anomaly detection models, which are the 1+SVM and the WBSN models. However, none of the optimization models demonstrate good performance on Pima Indians diabetes dataset due to the similar reason that explained in the previous slide. The high false benign rate is mainly responsible for this performance degradation, as indicated by the low recall value. Like classification models, in the case of anomaly detection model, we can see that the whale optimization performs slightly better than the other considered models. So this table shows the comparison between the convergence performance of the optimization algorithms of the BIOCAD framework for support vector machine based classification model and 1+SVM based anomaly detection model. The results indicate that the GRAILF optimizer performs best in terms of convergence speed, but the performance analysis has shown that the GRAILF performs the worst, which suggests that the GRAILF optimizer fast traps into the local optima. And here from the results it seems that the whale optimizer outperforms the Firefly and is not too much slower than the GRAILF optimization. Hence, based on the performance analysis and the convergence speed, it can be said that the whale optimization is the best choice for both the support vector machine and 1+SVM hyperparameter optimization. So these three figures shows the execution time comparison for the optimization algorithms in different settings for the support vector machine based classification model and the 1+SVM based anomaly detection model. The figures indicate that although the sizes of the datasets are considerably different, for instance, the University of Queensland vital sign dataset is 10 times larger than the other two. The execution time increased linearly. So it can be argued that the optimization algorithms are scalable and feasible to implement in a large-scale system. From the figure, it seems that the classification models take a lot less time than the anomaly detection model. So in this work, we presented a comprehensive framework for smart digital healthcare system, naming BIOCAD, with both patient status or disease classification model and anomaly detection model. So in our work, our particular focus was on support vector machine and neural network based classification model, DBSCAN and one class SVM based anomaly detection model, and we found promising performance for the whale optimization in comparison to Grey Wolf and the Firefly optimization techniques. We validated our framework using 3 state-of-the-art data sets, and we found 0.87 to 1 F1 score for the whale optimization algorithm. The experimentation demonstrates that the proposed framework is feasible to be implemented and is scalable for the large-scale systems for both classification and anomaly detection tasks. So in our future work, we will experiment with more promising classification models, anomaly detection models, and the optimization models for ameliorated model. Besides, in our upcoming work, we'll train the anomaly detection models with known attack samples for better outcome. Thank you for listening. If you have any question, please reach me out through my email address.